First, what happened to the calculation? Could somebody find what the error was? So we had done this problem of particles on a lattice, hardcore repulsion, but when they come on the same site, they have an energy epsilon. And then we did the calculation in the microcanonical ensemble and the grand canonical ensemble. And when I did on the Mathematica, I got two different answers. Did anyone try it out? It was just too tiring. Okay, well, if you have time and interest later, you can do. Now, there's only one lecture left, but I wanted to cover how would you do if I give you an interacting problem, how would you simulate on a computer? Okay. And simulation tools are very important because most problems are quite complicated and you cannot solve it analytically. So numerical tools are the best, one of the best ways to investigate the problem. There are two methods of doing problems with many degrees of freedom. One is called molecular dynamics and one is called Monte Carlo simulations. I will explain Monte Carlo simulations and the other one just name is molecular dynamics. So what is the motivation? So let me go through one more time. So we are in equilibrium statistical mechanics, we have no dynamics, only the Hamiltonian is given. You have a interacting system and the interactions between the particles or constituents are given. Then there is a recipe given for calculation. If I give you a configuration C with energy E and the system is at constant temperature beta 1 by kT, then the probability of a configuration is given to you. This we know from canonical ensemble that is proportional to e to the power minus beta E. So the aim of a computer simulation would be to create configurations C1, C2 randomly and fashion be able to give how to do that. But if C1 has energy E1 and C2 has energy E2, then the fraction of time C1 comes to be equal to beta E1 and the fraction C2 comes to be equal to beta E2. This is our aim, how to do. But before that, so then we have to introduce some dynamics to make the system evolve. And since we already decided that we need a probabilistic description, the dynamics will also be probabilistic. So it will be a stochastic process that evolves in time. And I'm a stochastic process. If I give you the configuration now, I do not know the configuration the next time step, but only probabilistically. So for that, the simplest dynamics is something called Markovian dynamics, which says the new configuration I can determine only if I know only the previous configuration. Okay. So the questions we like to answer is how to define the dynamics, how to simulate in a computer, and what dynamics will generate the correct equilibrium rates. Okay. So we will now forget about equilibrium starting for some time. I will tell you how to simulate any stochastic process on a computer. So how do you define a stochastic model? What should be given to define a model? First of all, you have to specify all the possible configurations the system can be in. So let me call them C1, C2, C3, C4, and so on. Then, to define the dynamics, I have to tell you what is the rate of going from configuration Ci to Cj. So given a certain configuration, I will tell you what is the next time step through something called transition rate. I will define the transition rate. But if I give you these two, then every time I know a configuration, I know the next configuration or next possible configuration or next step. So this is sufficient to define the model. So I've shown a C1, C2, C3, C4, C5. From C1 I could go to C2. From C2 I could go to C3. From C3 I could go to C4. From C4 I could go to C5. From C5 I could go to C6. From C6 I could go to C7. From C7 I could go to C8. From C8 I could go to C9. From C9 I could go to C10. From C10 I could go to C11. From C11 I could go to C12. From C12 I could go to C13. From C13 I could go to C14. From C14 I could go to C15. From C15 I could go to C16. From C16 I could go to C17. From C17 I could go to C18. From C18 I could go to C19. From C19 I could go to C20. From C20 I could go to C21. From C21 I could go to C22. From C22 I could go to C23. From C23 I could go to C24. From C24 I could go to C25. From C25 I could go to C26. From C26 I could go to C27. From C27 I could go to C28. From C28 I could go to C29. From C29 with rate W C1 to C2, but from C3 I could, from C5 I can go to C1, C2, C4 I can go to C5 and C5 to back and so on. But if I come to C1 I can only go to C2. Here's some example. So I use the word rates here. What is the meaning of rate? So when I say suppose an event occurs at rate lambda, suppose I say some radioactive decay occurs at rate lambda. It means in a short time dt, in a very infinitesimal time dt, the probability of that event occurring is lambda dt. So that's the definition. If somebody tells you that this event occurs at rate lambda, the meaning is this. Okay, meaning is that in an infinitesimal time dt, the probability of that event occurring is lambda dt. So if this definition is given, then I can ask what's the probability of the event occurring for the first time at time t? What's the answer? I have given you the probability of it occurring in time dt. I'd like you to answer if this probability is given. Now I have a system stochastic process. I tell you it occurs with rate lambda, and I want to ask what is the probability that the event occurs for the first time at time t. It does not occur for any time before that. Is it possible to compute? You have to think a bit also. Integral over. So we are asking, so there's a stochastic process. We are asking what's the probability event does not occur anywhere here and occurs at time t. If I do lambda dt, and if if the time is greater than 1 by lambda, then it becomes greater than 1. But it has to be probability, it has to be less than 1. I guess probability. No, that is not true, but anyway. But how would you do this? Given your knowledge of probability, if I want to know what's the probability does not occur in the first time dt? 1 minus? No, lambda is not lambda is a number, lambda dt is a probability. Okay, so let us first divide the time from 0 to t into many small dt's. Now I don't want an event to occur in the first dt, second dt, third dt and so on. What's the probability an event occurs in the first dt? Lambda dt. And what's the probability does not occur? So 1 minus, that is the answer. So therefore, if I want to ask that nothing occurs up to here is 1 minus lambda dt to the power t by dt, because there are that many intervals, then the event should occur. So that probability occurs in lambda dt. So it does not occur up to time t, and then it occurs in the next dt. So this is the probability. Okay, but remember dt is some small thing we introduced by hand. It should not come in the answer. So we should take the limit dt going to 0. So if I exponentiate this, this is like e to the power minus lambda dt into t by dt. This dt cancels out, and the answer is just that. So this is the answer. Okay, so the probability that it occurs the first time at time t is exponentially distributed. So sometimes when people define rates, they define through infinitesimal time dt or through waiting times, exponential waiting time. So both definitions are identical. From one you can derive the other. Okay, so this is point number 1. Okay. Now, so we have defined how many configurations are possible. Now we know what a rate means of going from configuration C1 to C2. Okay, summary. So summary. You can define in infinitesimal time, the probability is lambda dt, or you can define waiting times p of t, which is exponentially distributed. Okay. Now we want to generate random numbers. So first, if I tell you how do you do probabilities on a computer? If I say something occurs with probability 0.2, then what you do is you do generate a random number between 0 and 1, and then if it is less than 0.2, you say the event occurs, and greater than 0.2, you say the event doesn't occur. So that's how you'll do on a computer. And on a computer, usually a random number generator between 0 and 1 is available. So if I tell you that an event occurs with probability lambda dt, you draw a random number between 0 and 1. If r is smaller than that number, then the event occurs, else not. Okay. So that is when, so that we know how to do now. But what about distributions like an exponential distribution of this kind, and you are only given a random number generator in 0, 1. Okay. So sometimes, nowadays I don't know, maybe people use more like Mathematica or Python, where you can just say generate an exponential distribution. But still you might have some distribution which you do not know, and you are only given a random number between 0 and 1. So you would like to ask, how do you generate such distributions on a computer? So I can state it a bit more abstractly. Given the distribution for x and a relation between y and x, can I find out what is p of y? That is the question being asked. This we did earlier, but I will just repeat this one. Okay, so this is my probability distribution for x, this blue line, and this is some probability distribution for y, which is the blue line, which I want to find out. A given point in x, between x and dx, gets mapped onto some point between y and dy. So whenever an event occurs here, that event occurs here. But we know that whatever is the probability of an event occurring here must be the same as the probability of the event occurring here. Therefore, p of x dx is p of y dy. So whenever you map from one variable to another variable, this relation holds. So now we go back to our exponential distribution. Let p of x of x be the uniform distribution 0, 1, and py of y is this distribution. Now we have a reverse engineering question. What should y of x be? So we are given p of y, we are given p of x, and we want to find what the relation y of x should be. So that is simple. So I use the relation p of x dx is p of y dy. P of x is 1, so that goes away. Now I have to solve for y. So if I integrate this equation from 0 to x and 0 to y, I get some relation. So this calculation you should be able to do. And if I can invert and write y in terms of x, then my problem is over. So I take a random number between 0 and 1. Then I say, oh, if the number is 0.5, my y is actually 1 by lambda log 1 minus x. And I get an answer for y. And p of y will be exponentially distributed. So that's how, if you are given some unknown distribution, how you would generate on a computer, given a known distribution. Okay. I was a bit fast, but that's okay. Is this clear? It's clear. So now we come back to Markov process. This was so now I come to Markov process. So I'm given these configurations, they evolve stochastically. So what is the complete description of the process? I want to ask, what if I answer, I will completely describe the stochastic process. Now the configurations keep changing probabilistically, so I cannot expect to predict the trajectory. But instead, I'd be interested in asking, what is the probability of finding configuration C at time t? This question is the one, if I can answer, I answer describe the system completely. Okay. So now I'm interested only in the probability. C keeps varying with time, but this quantity may be well defined. So first of all, you have to ask, so then you ask, how does this probability evolve in time? And there is something called a master equation. It is an equation that describes how the probability of a Markov process evolves in time. And that is quite simple to this common sense equation. It says, suppose at time t, I have probability particle in C, there is a probability of Ci, of the particle being system being in configuration Ci. How does it evolve in time? There are only two ways it can evolve in time. One is the configuration changes from Ci to Cj, and the other is from some other Cj it jumps to Ci. These are the only two ways of this probability changing. When it jumps into Ci, the probability increases, and when it goes away, the probability decreases. So, this is an enumeration equation. It says it increases if I am in Cj and I jump to Ci, but that rate occurs with rate W of Cj to Ci. Okay. Then I can be in Ci, I can jump to some Cj, and that I am already in Ci, so that probability is Ci. Then I jump away from Ci. This enumerates the number of ways of going out of Ci. So this equation is called master equation. This equation will be important to us to figure out what dynamics we should give. Right now we are talking about general Markov process. Is this clear? This. Okay. So I will write this in a matrix notation. So P of C1, P of C2, P of C3, P of C4, a 4-state system. I am looking at the left hand side, which is this one. Now d by dt of P of C1 is the rate of going from 2 to 1 into P of C2, 3 to 1 P of C3, 4 to 1 P of C4, minus 1 to 2 into P of C1, minus 1 to 3 P of C1, which is just writing this out explicitly. Okay. So I have written it out for all the four equations explicitly. Two things to notice: the diagonal terms have to be empty, have to be negative. The non-diagonal terms have to be positive. Okay. So therefore, Wij is always positive. These are rates, probabilities. Wii is negative because there is a minus sign sitting in all of them. And the other thing you notice is that if I sum along a column, they are 0. Okay. So these are the only three properties. So the master equation looks like this: dp by dt is W, n cross n matrix times P, and I can give you any W that satisfies these three properties, and that will be a correct Markov process. So the non-diagonal element should be positive, diagonal element should be negative, and the column sum should be 0. Okay, so we defined a Markov process, we wrote down the master equation, and just by writing in a matrix form, we saw that these properties are satisfied. Okay. Now, how is it all connected to simulation? We'll come to that. Let us do some little bit of properties of Markov process. Now we have to be sure that probability should be conserved as we go along. This is something, okay. So let us explicitly show that the master equation satisfies conservation of probability. So this is my master equation: dp by dt is summation over j, wij, pj. Now I sum over all I. Why do I sum over all I? P of C1 plus P of C2 plus P of C3 plus P of Cn is my total probability. So I sum over all the i's on both sides. Here I can interchange the sum I and j. I can put this I this side and j this side. This is what I have done here. But wij. But when I keep j fixed and sum over I am doing the column sum. W1j plus W2j plus W3j, but column sum we know is 0, therefore we get this answer. Okay. So it says that probability is nicely conserved. So if I use a W matrix with column sums 0, conservation of probability is ensured. Okay. I hope so we have started with motivating ourselves by saying that we need to evolve our system as a Markov process, and now we are looking at some general properties of Markov process. Okay. Now, what are the other properties of W matrix? A few of them. this equation dp by dt is wp looks like dh by dt is h psi. No, d psi by dt is h psi. It looks a bit like Schrodinger equation. Only thing is, this W matrix need not be Hermitian. In general, it is Wij and Wj are not the same, so it need not be Hermitian. But we can, when we have the Schrodinger equation, what do we look for? We look for eigenvectors and eigenvalues. So it might be worthwhile to look at the eigenvectors and eigenvalues of W, just like we do for the other one. Now, one important thing to note is that when it's not Hermitian, the left and right eigenvectors need not be the same. So you must remember, sometimes suddenly you will find that one eigenvector, but you must be careful that the left eigenvector may not be the same. You should just keep in the back of the mind. So first statement, if I take 1, 1, 1, 1, 1, that is a left eigenvector. Why? What is the property of eigenvector? When I multiply that with the matrix, I should get back? Yes, so is it an eigenvector? Why is it an eigenvector? If I multiply this with the first column of W matrix, what do I get? The column sum. What is the column sum? 0. What about the second column? 0. So if I multiply this with W matrix, I get 0. So therefore, this is an eigenvector with eigenvalue 0. Okay. So 1, 1, 1 times any column is 0 because column sum is 0. Therefore, 0 is an eigenvalue and will denote its right eigenvector as PS of C. Sum. We do not know the right eigenvector. Right eigenvector could be anything, PS of C. Now, some statements I will make. We cannot show these statements. The first statement is that lambda 1 equal to 0 is non-degenerate. All entries of the right eigenvector is positive. All the other eigenvalues are negative. The real part is negative. So the largest eigenvalue is 0. Okay, so this is and the eigenvectors are orthogonal. Okay, so let me go through the important properties is for a W matrix, lambda equal to 0 is the largest eigenvector. Largest eigenvector, of course, because some of them will be complex. The real part is largest for that. All entries of the right eigenvector for this is positive. The left eigenvector is 1, 1, 1, 1, 1. So if I give you this many properties, how does the system evolve in time? So let us look at that. So just like we do in quantum mechanics, we do eigenvector expansion. I can expand this P of Ct in terms of eigenvectors of W. So let me write this as P of Ct is A1 times psi 1 plus A2 times psi 2 plus so on and so forth, where psi 1, psi 2, psi 3 are the eigenvectors of W matrix. And we know that if I do 1, 1, 1 from the left on P of Ct, there is one is A1, this is my eigenvector corresponding to 0. This gives you A1. It is orthogonal to all of them, so all of the others vanish. 1, 1, 1 is orthogonal to all the eigenvectors except its own right eigenvector. So I get A1. But LHS is 1, therefore this A1 must be 1. Why is LHS 1? Because we are summing over P of C. So A1P, irrespective of what you start with, must be 1. Okay. So now, I hope I made sense. Is that okay? Not okay. So I expand this is a column vector, P of C1, P of C2, P of C3 like that. I am expanding it in terms of the eigenvectors of the W matrix, psi 1, psi 2, psi 3, where psi 1 is the right eigenvector corresponding to the eigenvalue 0. Now, there is some coefficient A1, A2, A3, A4 and so on. Now, I take an inner product with the left eigenvector 1, 1, 1, 1, 1. Now, 1, 1, 1, 1, 1 into a column vector P of C1 plus P of C2, This will be P of C1 plus P of C2 plus P of C3 plus P of C4, but that we showed is always 1. So LHS is 1. Now I act 1, 1, 1 on psi1, that gives you 1. 1, 1, 1 on psi2 is orthogonal, it is 0, and so on. So right hand side I get A1, but LHS is 1, so A1 must be 1 for all time. Now the second thing to do is I look at the master equation. I differentiate on both sides dp by dt. I differentiate on both sides by d by dt. So RHS, I made this one. I differentiate A1t, A23, and so on. And here is dp by dt, which is w times p. Right? What did I write here? W times p, which is w times the whole thing. Is it okay? Remember, our master equation was dp by dt is w times p, and w acting on p is a1 times w psi 1 plus a2 times w psi 2, and so on. Okay. But w acting on psi 1 should be 0. No, what is that? Is an eigenvalue? Lambda 1 times psi 1 plus lambda 2 times, it is lambda 1 times psi 1 plus lambda 2 times psi 2 plus so on. But lambda 1 is 0. I made an error here, that is the thing. It is lambda 2 times psi 2 plus so on. So for example, so therefore if I take, and this is anyway 0, we took dA1 by dt is 0, it is 0. So now if I compare the terms one by one, dA2 by dt is lambda 2 times A2. So A2 is A2 of 0 e to the power lambda 2t. Similarly, A3 of 0 is A3 of 0 times lambda 3 of t. So I can solve for all the coefficients like this. And A1 we know is 1. So what is the net result? So your P of Ct becomes psi 1, A1 times psi 1 plus A2 e to the power lambda t psi 2, A3 e to the power lambda 3 psi 3 plus so on. But we know that the real part of all these eigenvectors is negative. Therefore, as time goes to infinity, you are left with psi 1. All these quantities go to 0. So that is the advantage of a Markov process. You start with any P of probabilities in the beginning. As time goes to infinity, you are guaranteed that it forgets everything about its past and goes to a unique steady state, which is the eigenfunction of its lambda equal to 0. Okay, I am guaranteed this property that, and that unique ground state or whatever, unique long time behavior, I will call a steady state. This is the name for that. And this is the eigenvector, eigenvalue 0 is independent of the initial condition. There are some caveats, true if system is ergodic and so on, but we will forget about that. Okay, what is the next slide? Okay. So I've told many things. So we started by motivating what should we do to simulate system in equilibrium. We shifted that question into doing a general Markov process, which could be not in equilibrium also. This is valid for that. And then we found out some properties of a Markov process, which said that in the long-term behavior, you always have a steady state, which is our equilibrium state in some sense, and that corresponds to eigenvector of eigenvalue 0. Okay. Now, so if I give you...
Sir, like in long time periods, does the system usually settle in the largest eigenvalue?
It corresponds to the eigenvector of the eigenvalue 0. The probability of the configurations will go to that eigenvector.
So it goes to the 1, 1, 1, 1 eigenvector.
That's the left one. The right one we do not know. The left one is 1, 1, 1, 1, 1. Right one we do not know what the answer is.
But the eigenvector corresponding to 0, it settles down on that vector.
So suppose you must forget about equilibrium statement. You may be simulating, let us say, um, uh, some stock market and agents interacting with each other or something. You only know the dynamics between them. You put them on the computer, you simulate like this, then you might reach a steady state which you do not know a priori, and often you get some unexpected results. If it is very unexpected, you can write a paper on that. Okay. Now, if you want to ask, what about the approach to steady state? It is controlled by the second eigenvalue lambda 2, which we will not bother about. So now, up to now, if it is clear, we want to ask, how do you simulate a Markov process? Every time you are in a configuration, you ask, what are the possible configurations you can go to? Let there be 5 of them. Then either you can do it in infinitesimal time, you increment time by a little bit, then it's either it goes to any of those 5 or remains at that configuration, or you can do in finite time. You take an exponential waiting time for all those 5 problems, 5 configurations, and then you choose the smallest of them and go to that time. Okay. Either way you can do, and that is that. I don't know. Okay. This I think speed of routines will wait. Recap. So let me recap one more time whatever we said. Markov process, what should be given to define a model? The configuration C1, C2, C3, C4, the transition rates W are going from Ci to Cj. Then there is a master equation, dp by dt is W of P. P is a column vector, probability of C1, C2, C3, Cn. Wij are the rates of going from Cj to Ci, column sums 0. Then the long term behavior, the system goes to the steady state, is a unique steady state, eigenvector 0, eigenvector of eigenvalue 0 is independent of initial condition if the system is ergodic. Okay. Okay. So whatever I told you up to now, you can use it to simulate any Markov process. Now we come back to our original motivation. How do we use this to simulate equilibrium systems? The equilibrium system, remember, we do not know what are the rates. What is given to us is the equilibrium probabilities. What we discussed up to now, the rates are given and you find out the equilibrium probabilities. Okay, no specific dynamics. Now question is reserved. We know that the long time behavior P steady state is e to minus beta E. What is the dynamics that gives the above? So the question is now reversed. Given a particular steady state, you have to guess what dynamics I should give so that I reach that particular steady state. Okay. So now there is some particular. Is the question clear that now we have reversed the question? Okay. There is something called detailed balance. So first statement we know is that steady state of a Markov process is unique. Therefore, if we find one solution to the master equation, that's a unique solution. Because of the uniqueness, I have to just find one solution. So suppose so in the long term behavior, nothing changes with time. I put this to 0 and I put this to 0. I need to know what W's satisfy dp by dt equal to 0. I should make right hand side 0. So suppose I take this pair by pair. I say I look at configuration Ci and Cj. There is a rate of going from Ci to Cj. There is a rate of going from Cj to Ci back. I demand that probability of going from Ci to Cj, which is P Ci probability of Cj into W Cj to Ci. This should be exactly equal to the probability current from Cj to Ci. W Ci to Cj, the opposite I have said. So suppose I demand that the probability current from I to j should be exactly same as the probability current from j to I for all pairs ij. That condition is called detailed balance condition. If that was satisfied, each term will cancel out to 0, the right hand side will be 0, the left hand side will also be 0 therefore, which means we have a steady state. So if I choose my rates, if this is satisfied, I have a steady state. Because I've made the right hand side 0. And this condition is called a detailed balance condition. It says that pairwise probabilities are conserved, probability currents are conserved. Okay, now I will, for simulating equilibrium systems, people typically use detailed balance condition. So what they will do is, but I know P of Cj and I know P of Ci. They are given by the Boltzmann distribution e to the power minus beta E by Z. There's a beta missing here. Therefore, now I know my final answer. So what should Cj to Ci be to satisfy? What should I choose for WCj to Ci? That is the question to implement on my computer. Comment about equilibrium, non-equilibrium, I'll skip. Okay. So now, is it at least some of you following up to now reasonably clear? Okay. So let us look for a convenient rule that is given is something called a metropolis rule. It goes by the name metropolis. So at some point in the evolution, you are in a configuration with energy E old. Then I make some dynamical move. I change something in the configuration, and that goes to a new configuration whose energy I will call as E new. And then the difference in energy is E new minus E old. It could be 0, negative, positive. We are just changing the configuration to new configuration and asking what is the change in energy. Then this metropolis rule says, if the energy lowers, you always go to the new configuration. If the energy increases, delta E is positive, then you accept that with probability e to the power minus beta delta E. I have written in the min-max form. It says if, forget that. If the energy is lowered, you accept probability 1. If the energy is increased, you accept the probability e to the power sometimes you reject the move. So the statement is that if you follow this dynamics, then the system obeys detailed balance. Why? Is there a why there? Yes?
We are going to the lower energy state is 1, so you would actually reach a steady state. Yeah, everything will go to 1, right? I mean, it will always reach out the lower state. So
yeah, but we are not trying to minimize energy in a canonical ensemble. Energy can go up or go down. It has a higher probability of going down. That's what you're saying.
Yes.
Yeah, because it agreed. But we need to show that if I use this rule, my detailed balance is satisfied. So I've given a small argument here. So suppose the E old was lower than E new. So I am right now in E old. My new configuration is energy E new. Therefore, my acceptance probability by this rule is e to the power minus beta into E new minus E old, which is positive, which is by this rule, metropolis rule. Now, all that we have to check is the detailed balance satisfied? So, what is probability of E old, W of E old to E new? It is the probability of E old, e to the minus beta E by Z, into the probability of going to the new one, e to the power minus beta E old, E new minus E old. Then this E old and E old cancel out, and you get this answer. Now we look at the reverse probability current, probability of E new, W of E new to E old. This is 1 because we are lowering energy. So this is just probability e to the power minus beta E new by Z, and they match. So detailed balance is satisfied. So if I chose metropolis rule for a generic system, I am guaranteed that detailed balance is satisfied. So if I run this run a simulation with this rule, at a long time will generate configurations with the correct equilibrium weight. That is the claim. Okay. Okay. I, um, how many of you are familiar with the Ising model? Not many. We'll skip then this. So I think we should just summarize one more time. So I told you how to simulate a Markov process. But to simulate a Markov process, you need to know the rates. But for a system in equilibrium, we are not given the rates, we are given the steady state. So we cooked up one rule. It need not be the only rule, there can be many rules. We cooked up one rule called Metropolis rule, which tells you rates, which will give you the given steady state. Okay. So I will skip this Ising model. So of course, so now I take some system, it has energy E, and start evolving the system on a computer. Initially the energy vanishes like that, it wanders around like that, and after some time it will start fluctuating about some mean value. Because we have to wait long enough times to reach a steady state. What is long enough? We do not know. It could be infinite time. But this is how a general plot looks like. But you have to have some mechanism to check whether system has reached steady state or the system has equilibrated. So you have to run the few different initial conditions to see where the curves they lie on top of each other. That's the only way to check. And the other way to check more quantitatively is to look at two-point correlation functions of this kind, expectation value of E of T1, E of T2, of various T1, T2, and they should be a function of only T1 minus T2. But these are when you do simulations, you will figure out these things. And you must also remember that when the system size increases, number of particles increase, the time taken to reach steady state typically also become larger and larger. So it becomes more and more difficult to do larger systems. So you'll have to figure out how to do. Second point is that when you do define thermodynamics, you're talking about 10 to the power 23 particles, a huge number of particles. But in a simulation on a computer, you cannot do so large a particle. You can only do finite systems. So that your answer will never be exactly same as what you would expect theoretically. So for example, if the black line is what you should expect theoretically, your simulation might look like this. And similarly here, there's a divergence for some quantity, but your simulation, which are the red dots, will have some difference. So you'll have to figure out how to go from simulating finite system sizes to infinite system sizes. That you'll have to figure out how to do some extrapolation and so on. Okay, so now coming back to so I thought that even if one doesn't take back much, if one just takes back a few things from the lectures. One is how to do a calculation with just those three rules, few rules we discussed earlier. The second is how to do a simulation on a computer, so that even without any other knowledge, one should be able to simulate an interacting system. So the basic Monte Carlo technique I described. So now in the remaining 10-15 minutes, what I will do is I will tell something a bit more advanced than this technique, which if you know the name, if something happens and you get stuck at a problem, you might remember this name and look at it again. Okay. So let me go through that. Yeah. So this was our Metropolis rule. So we are now going to discuss some other simulation technique for equilibrium static problems. But for that, let me just go through metropolis rule one more time. So I had energy E old, I have a new configuration with energy E new, and the difference in energy is E new minus E old. And they had a way, you accept a new configuration with probability minimum of 1 comma, whatever is the weight of new by weight of old, but we knew weight of new was e to the power minus beta E new, weight of old is e to the minus beta E old. That gave us this expression. This acceptance rule obeys detailed balance. And one thing to remember is that each simulation is done at a fixed value of temperature. Okay? Temperature is fixed and you are running over a long time. So we come back to the partition function. The partition function Z is sum over all configurations e to minus beta E, but I can rewrite it as saying sum over energy is E, G of E, e to the minus beta E. Where G of E I will call as density of states or number of states belonging to energy E. If I know Z, I can compute expectation value of e to the power n. This is sum over e to the power n G of E by Z. Given a probability, I know how to compute all moments. Now suppose I gave you G of E. If G of E is known, then the data for the whole temperature range can be found in one go. I don't have to do simulations at various temperatures. I just have to use this formula to find the answer in one go. So if I had to do 100 temperatures earlier, I could have to do just one simulation in this one. In regular Monte Carlo, each temperature has to be simulated separately. So the question now you can ask is, can I determine this density of states in a Monte Carlo simulation? If I can do that, I can run, I may have to do 100 less simulations. Is this clear? So now what I will discuss is some algorithms people have put forward to determine this density of states. Okay. So those are called, we earlier called metropolis, now we will call them flat histogram methods. Okay. Suppose previously we had assumed, is the motivation clear? So we have now changed the motivation. Now we are not doing a fixed temperature simulation. We do not know the final probabilities anymore. We are going to choose dynamics so that we think we can compute the density of state G of E. So suppose your weight of a energy configuration, weight of a configuration with energy E was no longer e to the minus beta E as given by the canonical ensemble in the canonical Boltzmann distribution. It is some weight. We will not fix it. Suppose it has some weight, but we run a simulation satisfying detailed balance with metropolis rule. Probability of accepting a new configuration is minimum of 1, weight of new by weight of 4, which is the exact metropolis rule, but we no longer use that it is equal to e to minus beta E. That's the only difference. You run a simulation like this. After some time, it goes through various energy values. Every time it goes to energy E, you update a histogram by 1. So you maintain how many times have I visited energy E, and I'll call this as histogram H of E. Now, given the weight of a configuration, I can ask how many times, what is histogram going to be? If the weight of a configuration of energy E is 1 by weight of E, and there are G, the density of states is G of E, then the histogram will be proportional to number of configurations of energy E into weight of each configuration. Therefore, it should be proportional to this quantity. Whatever weight of E is. If weight of E happens to be 1 by G of E, then histogram would no longer depend on energy and the histogram would be flat. Okay. But of course, one does not know G of E, but one could use the fact that if the correct weight of E was chosen, that weight of E was 1 by G of E, then the histogram would be flat. We will use this particular aspect to figure out what is the correct G of E. Okay. So what is the idea? The idea is that I run a simulation with some random weight, W weight of E, then I measure the histogram, and I know if my histogram is flat, then my, if I choose my weight of E to 1 by G of E, and the histogram is flat, I have chosen the correct G of E. Okay, let us do an example. So, we do not know when you start the simulation what is the density of states. So, you make a guess. Your G of E is G1 of E, something, maybe constant, maybe some parabola, something. And then you say, given the G1 of E, your weight of E is 1 by G1 of E. And then you know your histogram should be G of E times weight of E. So this is the actual G of E divided by your guessed value G1 of E. So histogram will look like this. So now you have a simulation with your guessed G1 of E, and you get some histogram. Now if I take the G1E which I know, which I have guessed, this side, I will get my G of E. So G of E is weight of E with G1 of E. Theoretically this is the right answer. You have got it. But you can make a guess for this G2 of E. When you run the G2 of E, generate G3 of E, and you have the right. So in principle, I could if I were doing a system of size 8, if I start at this time step, I have the right. Let us see if I do this for some system, what do I do? Don't worry, this is for some model. We don't have to know what the model is. Model. So let me describe this plot. This is histogram. This is N. N is like number of participants. N goes from 0 to 5. So after one iteration, the histogram looks like this, and density of state looks like this. After two iterations, density of state looks like this. Flat in some region, histogram is flat up to here, it improves up to here. But after 11 iterations, it became here to 16 iterations here, 21 here. And so the density of states kept improving, but it is not getting the right answer ever. Have I completely lost everybody or not? Lost. What am I plotting? Histogram. So what I am doing is I am taking some model. I make a guess for G1, density of states. I run the simulation. During the simulation, I ask how many times I visited state N. Here it is E and there is N. Then I find out, multiply G1 to this side, I guess what is G2. That's my first iteration. Then I put G2 back here. I multiply G2 into H of E, I get G3 and so on. That is what I am doing. And as I do more and more, I see my histogram becoming more and more flat in the region it is. And I know if it is flat, the answer must be right. So I am getting the answer flat up to a certain region and then it is not anymore. If I had done for many more iterations, it would have become flatter and flatter. And if I can measure G of E, I can do the problem in one go. But clearly this is not a very fast convergence. So there is some improvement. So I will describe this algorithm also, Wang-Landau algorithm. Even if you don't follow the thing, important thing is you can remember the name Wang-Landau algorithm. It is quite a powerful algorithm. So in the previous one, so it makes the change that your density of states now continuously evolves during the simulation. But it improves the convergence issue that was here. It is going to improve dramatically, and it's a very popular and efficient algorithm. Okay, so let me give a algorithmic algorithm. Let me describe the algorithm. You start with a flat density of states, histogram is 0, you change the configuration to another one, you accept that with the same metropolis rule, probability minimum of weight of old, weight of new by weight of old, but weight of the thing is 1 by G of E. So this is exact metropolis rule. Then when you come to the new configuration, you update the density of states of that configuration by a factor f, and you update the histogram there. So my system is evolving in time. I come to energy E old, then I go to E new. When I go to E new, G of E new is updated and H of E new is updated. Histogram you have to always update, and so is the density of states updated. You keep doing this, and every time you check, there's no arrow going out. After doing for a long time, you check, is the histogram flat? Of course, nothing is numerically always flat. If it is roughly flat, if it is not flat, you keep doing it. If it is flat, you come here, and then you reduce this factor by some root of f. So now your histogram is roughly flat. The next time step, you make it even flatter. Then the next iteration, you make it even flatter, and so on. I did this very fast, but remember the name, this one. You can always look it up somewhere. Yes? Yeah, so f you choose some factor of some number, let's say 5 or 2, something in the beginning, then it becomes 1.4, then it becomes root of that, root of that, root of that, and go on. Yeah, so then after some time, we are most of the time interested, G of E is a large number. Most of the time we are interested in log of G of E, which is like entropy. So it's log entropy, entropy is entropy plus log f. So as f becomes smaller and smaller, you start updating the third decimal place, fourth decimal place, eighth. So after some time you feel that you have got the first 6 decimal places right. Then you say, this is what I wanted. So that is, okay. So let me show you the power of this algorithm from their paper. So this is some, so this, we have not discussed Ising model. So let us say it's some model. What is plotted here is that model is solvable. So you can have an exact answer and an answer from simulation. So this black line, black line is simulation and dotted line is exact. This is for a 32 cross 32 lattice, and this is 50 cross 50 lattice, and you can see that there is no difference. The error is so small, error is of the order of 10 to the power minus 4. So it has got it very well. If you measure some specific heat for Ising model, the black line is the exact answer, or black line is a simulation here and dotted line is exact, and you cannot make out the difference. So once I measure G of E, the whole temperature range I can get in one shot. So there is no more simulation being done, and you can see the error is extremely small. Okay, so this particular method I find extremely powerful. So sometime if some of you happen to do simulations of this kind, the metropolis rule is the standard one, but these non-standard ones are actually very powerful. Okay. Oh, that's where I stop. That's it. So then I have to summarize. Yeah. So let me summarize. So today's lecture, what we did was, given any stochastic process, given a Markov process defined through its configurations and space, I described how one should go about simulating them. Then we fine-tuned them for equilibrium static problems, where the steady state is given and you have to guess the rates. And then we discussed a method where I don't even worry about the steady state, I just try to figure out the density of states directly. In the previous lectures, we focused on, we didn't worry about how the rules come about. We tried to summarize what are the rules of calculation, so that if one wants to do something, forget about where they came from, what is the motivation for them. I try to summarize those rules. So I hope that with these, you can do something by yourself at some point. Take some problem of interest, either do on a computer or do some small calculation, and that helps you to learn things faster. So I'll stop now, and any questions I'm willing to take. Yes.
I didn't quite get the idea of flattening of histogram. Like, why do we need to do that?
Right. Because we are choosing, as the system is evolving in time, as the simulation goes forward in time, your G of E keeps changing with time. Now, how do we know that we have reached the correct G of E? But remember that every instant we are choosing that the weight of a configuration is 1 by G of E. So if we reach the correct G of E, then the histogram will become flat. So every time we look at the histogram and say, the histogram is becoming flatter, which means we are converging to the correct G of E. So this is just, but of course, you see that histogram, this is a numerical answer, it can never be a line. It goes up and down like that. So you have to say, at some point you have to make some measure and say, this is a flat histogram. And when I stop there, then of course, there is no way to say you got the correct G of E. As an example, if you do this, you say this is the correct G of E, then you trust the simulation.
So if I'm not wrong, like using the histogram, we try to get the weight for each probability states and then try to simulate the model in general.
No, we are simulating the model and using the histogram to get the correct density of states. And if I get the correct density of states, then I write them down and then I do the sum, I do this, I just do this I just do all these moments by just calculation. I don't have to simulate them anymore. It's only a numerical calculation. The simulation takes a lot of time. So it cuts down the number of simulations by a factor of 50 or something. Any other? Padmanath had a question. Yes.
Well, half of this is also new to me. On your flow chart thing, so G of E is actually a function of E, right?
Yes.
And F is basically some constant that you are going on varying as per your iteration, as I understand, right? Now, how do you, what is your initial guess for E to start with?
G of E.
Yeah, G of E, G of E.
Yeah, you can just choose a flat one. You have nothing else to choose. It is not correct, but you can just choose a flat G of E.
Yeah, but then how will you get all the features of the actual G of E if F is just a constant?
That is the point. The dynamics keeps driving it to low probability states. And you will see, this plot, you start with a flat histogram. This blue line is the one at 5 iterations. After some time, you can see it quickly converges to a flat one. So if I had a corresponding plot for G of E, you would see it go from G of E like this, and the second iteration itself, it starts mimicking the actual G of E. If you were to do on a computer, you will see it starts converging to the actual G of E very fast. All the details come out, even you get quite fine details, even, if, for example, if there is a non-convexity, even that is captured quite well.
Okay, thanks. Let's say in a different system, now a 3-dimension system,
Yes.
2 dimension for the space and 1 dimension is for the time. Let's assume Mingo's or 3 plus 1 dimension. What can these things to be applied on this?
It can be, but the thing with the, I don't know Q's, whether I should call lattice simulations.
Yeah.
The weights become imaginary, often. Then there's a problem. If otherwise dimension is not important. Okay. Any dimension I can do 2-dimension, 3-dimension. But if the weights are not real or not positive but imaginary, then it becomes a problem.
But here, you still have a probability.
Because the probability comes in this one.
Yes.
Otherwise, it will work perfectly well.
Okay.
But that is the issue with such things.
I see. But you can actually still work with the Euclidean 3 plus.
I do not know. Once I was discussing with somebody, I realized this was the problem, but we can talk about it and check.
Yeah, okay. Yes. We can talk about it later. Thanks. Sorry.
Yes.
Earlier, when we were discussing about Markov model, we said like after a long period it goes to the steady state.
Yes.
And usually, like we cannot like when we do it in computation, we have to do it for a finite time period so that we get to know it. But like to pick a proper time period, can we use the eigenvalue to get a characteristic time scale on where it will actually
Yeah.
end up as a
But
steady state?
if I want to use the eigenvalues to determine what's the typical time scale, I need to know 0 is the largest eigenvalue. Then there's lambda 2. I need to know lambda 2. That was only then I just, because that time I thought nobody was, I was not describing well, I just jumped the thing at that. So this was the long time. So when I look at the eigenvalue expansion of the probabilities, it is psi 1 steady state plus the next eigenvector plus next one. The next one looks like a2 of 0 e to the power lambda 2t psi 2, a3 lambda 3 and so on. Now lambda 2 is the next eigenvalue, next one is like lambda 3. So last times I'll drop these quantities, I'll just keep first two. So this is PS. So when I take P of Ct minus PS, the steady state, the difference is e to the power lambda 2t. So now I can ask, when does the difference go to 0? When times are much larger than 1 by lambda 2. So 1 by lambda 2 is your time scale. And lambda 2 you will realize goes as 1 by n to the power something. So it will go with system size larger. But if I happen to know lambda 2, so if I were to characterize the long time behavior, I will try to calculate lambda 2. But on a computer when I do, either you can do that or you can just wait for a long time and see, you can estimate lambda 2 by doing for different system sizes and trying to find out when does it reach a time independent value.
Also, I have one more doubt, like how do I initialize the weight matrix, like W?
W matrix you cannot initialize. W matrix is the definition of the Markov process.
But how do I select it in general, like using lambdas or like?
No, that it depends on your system of interest. You can, if I tell you, I cannot tell you the rates. Only thing I can tell you is that it should satisfy these properties. It should satisfy these three properties. If it satisfies these three properties, you are guaranteed all those other properties. We will call it the Markov process. But we are not doing a general Markov. When we are going to do something, if you are a mathematician, that may be enough. But if you are going from a physics side, you will first look at the system of interest, define lambda W's, and then analyze forward.
So here in this case, W's are not time dependent, right?
They are not time dependent. They were fixed with time. True. If they were time dependent, then all these properties will not hold. Because now, what is steady state? No, because things are keeping on changing with time. That is true. But sometimes the rates, W's are time independent.